All right, let's start. So we're going to pick up from last time to talk about Kruskal-Katona. So let's quickly recall the definitions needed. We have in Kruskal-Katona, we have the notion of shadow. That's what we cared about. We have K family, and the shadow is one uniformity lower, is K minus 1 set. This is all K minus 1 set lying in some F in F. So Kruskal-Katona is saying even the size of the family, what we want to do is to minimize the size of its shadow. And the precise formulation, let me write it down, remind you, it's for every, we have a sequence of a strictly increasing number, nk bigger than nk minus 1, bigger than ns, at least s, at least 1. We let m to be the sum of these binomial coefficients. Then the conclusion is for any set f, for any system of sets f of size m, K-set family with size of m, the number of sets being m, then we have its shadow as K minus 1 set family must be at least. So what you're going to do is very simple. You just subtract 1 around here. Nk, choose K minus 1 plus Nk minus 1, choose K minus 1 minus 2, I think, plus n is s minus 1. All right? This is what we want to prove. And last time we mentioned the technique is this technique called shifting. So what we want to do is, we're given an extremal problem, and we want to minimize some invariants. Here is the size of the shadow over all families. The generic family could be really wild. The idea is we're going to do some shifting operation to make them more structured. And here, what we want to do is to exchange large elements by small elements so that it will look more like the Collatz ordering that we defined last time. But the actual proof goes a little bit different. The proof we will see is that we will not do shifting so that it becomes completely initial segment of Collatz, which would have been done. There is a way of doing this, but not so trivial. You have to be a little bit careful with the shifting. So we're going to do with a combination of shifting, you get some structure, and we're going to use induction to finish the proof. And this proof is relatively relatively short. So let's recall the shifting operation we defined. So the idea we're going to use shifting to get a new family to have some structure, and then plus induction. So here's the shifting operation. We're going to fix some for I between 2 and n. We're going to exchange large elements. By large, I mean anything from 2 to n. And we want to get rid of I and put 1 in there, if that's possible. Okay. We shift these elements in our set system using pivoting on element I. So the definition is we're going to delete I from it and add 1 to it. Okay. If this is a legal operation, by legal, we mean that the resulting set is still a K set. So when is it still a K set? When I is in F and 1 is not in F, right? And also, we don't want to end in the set after this operation. If this is already in F, that's not good because we are not preserving the size of the family. We basically shift one set in F into another set in F. So if this is also in F, we are losing one set. We are changing the cardinality of the collection. So also we require, and this new set is not in our original collection. If either one of these condition violates, we don't do anything with this shift. So let F just to be F, the shifted one just to be F. Good. So then we can write, we're feeding a family F, we write SIF to be the new family obtained by applying this I shift to all sets in F. So this equals to SI of F for all F in our family. And by our definition, it remains a K-uniform family. Also, we don't collapse two sets into one, right? If the shifted one is already in the family, we don't do anything to it. So we do not change the cardinality. In other words, this one has the same size as our original family. That's not hard to see. So this is the family. So we will call F compressed. Compressed means we swap as many large elements by small elements as possible. If when you try to swap it, you will not change it anymore. Okay. For all I from 2 to n. So keep operating this, keep changing F without changing the cardinality until you cannot anymore. So until when you're performing it, you get the same family. We say it's compressed. So here we have to be rigorous. We have to show that this process will terminate In other words, how do you know we are not shifting back and forth? How do you know we will eventually arrive to a compressed family? It could be that you just change back and forth between two families. There is a way to prove this. There are several ways to prove it. I will leave it as exercise for you to show. So exercise, think of a way to show that for any k-set family F, it is a finite process. When you apply this I shift, this operation, and then in arbitrary order, eventually you will arrive at the compressed family. Exercise. Prove that it is a finite process to shift any family F to a compressed one. Okay, here the hint is that we can use weight functions. We can give weights to the sets based on what element it contains. If it has, for each element from 1 to n, you give weight, all right? Larger elements has larger weight. Then the weight of a set is just the sum of the weight of elements in it. And the weight of a family is just the sum of weight of sets in it. Now, when you perform this operation, shifting, you are swapping large elements by smaller elements. So the weight is strictly going down. And the total weight is finite because the whole family is finite. So you cannot keep strictly decreasing the weight. Eventually, it will drop to, I don't know, you cannot drop below 0, right? So if you keep decreasing, this process must be finite. That's already a proof. So try to write it down more rigorously. Good. Let me give you an example of shifting. So an example would be, let's do F is, let's say 1, 3, 4. I have a family here already. Let me use the same one. 2, 3, 4, and 2, 4, 5. Okay. Now we're going to do a S5 shift. Meaning, whenever we can swap 5 by element 1, we're going to do that. As long as the shifted one is not already in the family. So to do this, the set itself must contain element 5. And element 1 is not in there. If you go through the list, the first set has no even 5 in it, so we cannot do anything. The second one, it does have element 5 in it, but 1 is also in there. So we cannot shift it either. We need 5 in it, and 1 is not in it. So this one also remains the same. The third one does not even have 5 in it, so same. Last one is eligible. There's 5 in it, 1 is not in there. So we're going to delete it and add 1 in. And then we're going to check whether 1, 2, 4 is already in the family. No. So we can shift it to 1, 2, 4. All right. So you're going to swap 5 and adding 1. Any question? So here a remark is that the initial segment of Collatz order are always compressed. If you're not convinced, try to write down some initial segments for some value of k and see it yourself. But the problem is not all compressed families are initial segments of Collatz order. The other way around is not true, unfortunately. But that's what I said, but not all, not every compressed family is initial segment of Collatz, unfortunately, which means that we have to work a little bit harder. We have to work a little bit harder. So let me give you an example of a compressed family that's not initial segment Collatz. All right. So here's an example. What's an easy way to come up with the example? Let's take k equal to 3, let's say. Or even just k equal to 2, very simple. You have a set of pairs that's compressed. That means you cannot shift it anymore, but it's not the initial segment of Collatz. So you can just take family as long as, look, we want it to be compressed means we cannot perform any SI shift. When we have to, what's a necessary condition to apply shift? 1 cannot be contained in the set. So if you choose a set where choose a family where every set contains 1, then you cannot perform shift to it. It's already compressed. Okay, so that's what I'm going to write. You can choose 1, 3, 1, 5, 1, 7, 1, 9, right? Let's say just these 4. No matter for which I, you cannot shift it because I1 is in every set. So this is compressed. Not all is lost. We still have some structural information about these sets, about compressed sets. So we're going to make use of this structure, and then we're going to use induction to prove this theorem. All right. Any questions so far? So here's how we're going to do it. Let's first observe some observations. These observations are not hard to prove, but tedious to write down. So I will leave it as exercise for you to verify yourself. None of them is hard, right? Just try to check by definition how we define shifts. Everything will become clear. So the first observation is observation or proposition. So I will leave the following propositions as exercises. The first one is the shifting operation does not change the cardinality. So for any f, for any I, this map, this shifting map, mapping from original family to this SI shifted family F is injective. So in particular, they have the same cardinality. This should be very clear if you go back and check the shifting operation. we never shift one set to another set that's already in the family. So same cardinality. As we mentioned last time, what we want to do is to prove a lower bound on the size of the shadow. So when you perform this shifting, we want to keep the cardinality of the sets of the family. And also, meanwhile, we do not want to increase the size of the shadow during this operation, because if you increase the shadow, you could have this new family have larger shadow than the original one. Then proving lower bound on the new family's shadow has no meaning. We want the other way around. We want this new family's shadow. We want the new family's shadow is at most that of the original one. Then proving a lower bound on the new family's shadow can be carried over to lower bound of the original shadow. That's the next proposition. This shifting operation does not increase the size of the shadow. Shifting does not increase the size of shadow. Proposition. Same hypothesis for any family, any I. So how do we prove that we do not increase? Actually, if you work a little bit, you can prove something slightly stronger. You can prove that if you do the shifting, you get this new family. Now you check its shadow. We want to prove that this is at most the original shadow, right? So you can actually prove that this is actually a subfamily if you swap these two operations. If you take the shadow of the original one and then you shift it. This is not hard to prove. I hope you can check it yourself. This implies what we need. Why? Because in particular, that implies the shadow of the shifted family is at most the shadow of the shifted family of the shadow. But by previous proposition, the shifted family has the same size as the original family. So this is the shifted family of this guy. It has the same size as the original family, which is just the shadow. So this equals to previous proposition size of the shadow. And that's what we want, right? The new shadow is at most the old shadow. Good. We need one more observation. This observation will be used in our induction. So let's think about it. We want to use induction. What will be the natural thing to induct on? The natural thing to induct on is sort of the dimension, the ground sets. We have n elements. If somehow we can derive some new family with one element in the ground set removed, then we can induct on it. So we need to somehow decompose the original family into families on smaller ground sets. And there are some natural ways to do this. We're going to do the following one and then observe something about this new family. So this is how we're going to do it. so we're given this F, K set family. We first split, so we want to get rid of an element. Let's just fix element 1, the first one. So we can, then naturally we can partition F into 2 subfamilies, those sets containing 1 and those sets that do not contain 1. So we can write F as F1 union F1, its complement. So what is this? Where F1 is the subfamily containing elements 1. All right, and F1C is just those not containing 1. So if you think of subsets of n as the points on hypercube, what this partition is basically, you look at the one codimension 1 subcube, the one that contains 1, the one that does not contain 1, and look at these 2 codimensional 1 subspace, how they intersect F. And the intersection will be F1 for the intersection between the subcube containing 1. Its intersection will be F1C if you take the one that not containing 1, right? So now this is good for us. Why? If you look at F1C, already the sets in this family do not contain element 1. So we shrink the ground set size. We can use induction. But F1, not quite. The sets in F1 could have every element in N, right? So let me write down the thought process. Let's try to think, right? What's the thought process? So this guy is good, nice. 1 is not. F1C is on ground set N minus 1 with 1 removed. 1. So good for induction. Induction on the size of the ground set. But here, you could have everything. What we can do? Well, we can do, again, the injective map, a bijective map, in fact. We can just remove 1. Since all of them contain 1, you just remove 1 from everything. Now, we again go to the ground set one size smaller. And what's even better is that the uniformity also dropped from k to k minus 1. So you can even have a stronger induction hypothesis on this new family. Okay, so we can remove 1 from all sets in F1. Let's use a notation. What's my notation? My notation is L1, which stands for the link of 1. So L1 is F with 1 removed, where F comes in F1. So in other words, L1 is the link of the element 1 in the original family F. So the final observation we need to observe about these 2 family is the following. That's why we need compressed family. So yes, it will be a double induction on K and N. So let me write it. So this is a K unit, K minus 1 uniform. So here's the structural information we need from compressed family. If our family is compressed, then we know quite a lot about these two subfamilies we defined so that we can use induction hypothesis. We can use induction. The first information is, let's say this proposition heart. We're going to use it later. First one is that if you look at the shadow of those sets not containing 1, you will actually be anything in this shadow will be an element in L1, simply because F is compressed. Because if anything in here is not in L1, you can compress it. You can swap some large element by element 1 without landing in the sets that's already in our family F. That's already a proof, right? And the second one is that we can write down the family of our original collection. This will be, what's the shadow? Well, L1 is in the shadow, because L1 is the shadow of a subfamily of a special form. You remove element 1. And you can check that the remaining one that we haven't covered in the shadow, since F is compressed, you will, of the form E union 1 for some sets E, that's in the shadow of L1. This is also not hard to verify. Try to check it yourself. So the consequence of the second one is that we can now write the size of the shadow to be size of L1 plus, what's this size? This size is exactly the size of the shadow of L1. Okay, so the size of the shadow of a compressed family has a very clean form. It's equal to the size of the link of 1 plus its shadow. We can now put all this together to finish the proof. So we will do a double induction. First on the uniformity K, then on the size M. M is the size of the family. Okay. So the base case of the outer induction is K equal to 1. This is trivial. So the base case of the outer one, K equal to 1, this is trivial. Why? As the shadow of one uniform hyper singletons, the shadow can only be the empty sets. As shadow k equal to 1, yeah, it's trivial. A shadow of any one uniform family is just a single one, the empty set. Okay. So assume k is at least 2. Good. Now we're going to do, for the inductive step of k, we're going to do induction on m. Now we're going to induct on the inner loop, induct on m. The base case is m equal to 1. Let me draw some colors. We have induction on k. So this is induction on k, the outer loop. Now we're going to induct. We then induct on m. So inner size of m starts here. If m equals to 1, also there's nothing to prove because 1, since our family is k uniform, so k choose k means, so that means this is the base case, m equal to 1, right? That means f is a single set, as one set. And the shadow, if you have a single set of size k, the shadow is all k minus 1 set in it, which is k choose k minus 1, as desired. Good. So assume now m is at least 2. Now we're going to do compression. We do compression as much as we can. We may assume f is compressed. Now we may assume f is compressed. Why we can assume this? Here, I'm actually, I was lazy, sloppy a little bit. We have to use these two propositions. First of all, shifting does not change the size of the collection. Second of all, shifting does not increase the size of the shadow. So we can assume f is compressed. Okay. Or otherwise, we can keep shifting the family while keeping its cardinality and not increasing its size, its shadow size. Good. Now that f is compressed, we can then use the last proposition. Okay. And since we want to get a lower bound on the shadow, we're going to use this one, right? And then we can use induction on L1 because L1 is a smaller size and also one uniformity lower. You can sort of already imagine the rest of the proof. So let's write things down. We will, to finish the proof, we will need a claim, which will give a lower bound L1. If we have a lower bound L1, we can use induction hypothesis on L1, Kruska-Katona, we get a lower bound on its shadow. Together, we get the desired lower bound on F. So the claim is the size of L1 is at least nk minus 1, k minus 1 plus nk minus 2 minus 1, k minus 2 plus dot 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 ns minus 1, s minus 1. Proof. Suppose not. Actually, let me actually show you the claim. We'll finish the proof, then we come back and finish this claim, right? The claim, finish the Kruskal-Katona inductive step. And then we are all done. Why is this true? Well, by proposition part, the second part, we know that size of the shadow equals to the size of L1, the link, plus its shadow. Okay, then by the claim, L1 is at least this number. Plus, now you look at its shadow of L1. Because L1 is at least this, and L1 is k minus 1. L1 is k minus 1 uniform. So by induction hypothesis, the shadow of this is shadow of L1, right? Is at least plus this new one. Will be the same thing, but you remove one more from bottom. All right. We are done because now you can pair this up. For example, you pair this one with this one. Yeah. Dot, dot, dot. This one with last one with last one. What do you get? This is nothing but nk. Choose k minus 1 plus dot, dot, dot. ns. Choose s minus 1. Finishing the proof. That's the bound we want. Yeah, recall this binomial identity of binomial coefficient. If you want to choose k minus 1 guy from a group of nk guys, you can either choose this k minus 1 guy from all but one person, or you will choose that particular person that you exclude at the first case and choose the remaining one from the all but that person, right? It's a very basic identity. So we are left to show this claim. Let's see the proof of the claim. Suppose this is not true. We're going to derive a contradiction. Suppose L1 suppose not true. Then what we have is let's look at the family not containing 1. This is everything but with F1 removed. But remember, F1 is the same size as link of 1. We simply remove the common element 1 from all sets in F1. But now we assume L is smaller than this cardinality we claimed. So we get a lower bound on the size of this one. We get that this is strictly greater than the original family is this size. And L1 is smaller this bound that we're claiming, which is nk minus 1, k minus 1, plus dot dot dot, ns minus 1, s minus 1. And use this binomial identity, coefficient identity again, this equals to nk minus 1, choose k minus 1, it should be k, plus dot dot dot, ns minus 1, choose s. Good. Now, remember, F is compressed. What does it mean? That means the family not containing 1 is not everything. Because if it's everything, we can shift it. We can sneak 1 in, replace some larger elements. So in particular, the family not containing 1 should be strictly smaller than everything. That means we can use inner induction hypothesis. So inner loop is induction on the size. We can use induction on this guy. So induction on size of this, we get the family not containing 1, its shadow is at least, so you have this quantity, right? Minus 1, minus 1. That's Kruskal-Katona induction is nk minus 1, k minus 1, plus dot dot dot. ns minus 1, s minus 1. Okay. We are done because recall this. Why we cared about the shadow of the family not containing 1. This is a subset of the link of 1. So we have L1 is at least this quantity. This is a contradiction because we have L1 bigger than the quantity we want, while we assume that it's actually strictly smaller the quantity we want, right? That's a final contradiction. Finish the proof. There is actually a tiny issue here. Can anyone see where is the tiny issue? No one? The tiny issue is that, let's look at Kruskal-Katona. Last time I left it as exercise to say that for any natural number m, you can write it into this form. And in this form, a crucial requirement is that this is a strictly decreasing sequence. And this ns should be at least s size, which is 1, at least 1. So it could very well be that ns equal to s in our case. It could be that ns equal to s. Now you have s minus 1 choose s. Remember, the last one should be at least the size of at least this one. So this is not quite the form we want to write the size of F1C into, not this so-called cascade form, not the form in the hypothesis. So if this equals to S, you have to massage this a little bit. So try to fill in the missing bits. If this is not of the form, what you're going to do, all right? So here's a little issue. It's possible that ns equal to s, then this is not of the form in hypothesis of Kruskal-Katona. Okay, fix it. This is exercise. That's all I want to say about the proof. I did skip some details, but I think these details are standard to verify yourself. It's not particularly illuminating to go through these verifications in the course. Now, Kruskal-Katona, it's a very fundamental, important result. Let's see one of its application. We can use it to derive something we have already seen, another important theorem we've seen before, the Ehrlich-Corrado theorem. So let's see application. Kruskal-Katona implies Ehrlich-Corrado. We actually just need to use the simplest form of Kruskal-Katona. That's the form that we only have one binomial coefficient. The simplest form, I'm going to use the baby case. Baby Kruskal-Katona says, if your family equals to some n choose k, then your shadow is at least n choose k minus 1. Yeah. So let's recall what is, do you still remember EKR, the Ehrlich-Corrado? He says that for k uniform intersecting families, its size cannot be larger than m minus 1 choose k minus 1. Intersecting k family size is at most m minus 1 choose k minus 1, with the largest being all k sets containing a fixed element. What's the idea? So we want to prove an upper bound on intersecting family. Somehow we have to use that if a family is large, its shadow is large. Okay. Here is the idea to get shadow involved. The idea is, let's look at this family. We've seen this before. This is the family that containing all the complement sets, complementary sets in our original family. The key observation here is that we cannot have an element for any f in F and F prime in the complementary family. We cannot have impossible to have one as a subset of another. Why is this true? Just draw some picture. If F, okay. To make it simpler, let me write F hat bar. That just means, this just means M minus F hat. So what do we know? We know F hat, oh sorry, F prime is also in F, right? It's impossible to have this because if F is in this F prime hat, where can F prime go? F prime is this outside, right? This is F prime. That means F prime and F is disjoint. That's a contradiction because our original family F is an intersecting family. Good. Now we can see how we can finish the proof. So here's the idea. So suppose if F is large, but this is the same size as its complementary family. So if this is large, it will imply the shadow of this is also large by Cruz-Cacatola, right? You keep applying for the shadow operation, the shadow is large. But the shadow of this guy, since we cannot have any of its elements containing an element of the original collection, so the shadow of this guy is disjoint from this family. I'm running out of symbol. What's the symbol? Apple. But by the apple, we know shadow of F is disjoint from F. But this shadow is large, which none of which is in the family. So that implies F must be small. That's the contradiction. Okay. Let's write down these details. So suppose not. Suppose Erdős-Corrado false. That means our original intersecting family is strictly bigger than n minus 1 choose k minus 1, which then, so we have the complementary family equals to F bigger than n minus 1 choose k minus 1. But the complementary family is a n minus k uniform family. F is k uniform. the complementary sets m minus k are of size m minus k, it's more natural to write its size as m minus 1, m minus k. So let's write in this form. Now, by Cruz-Cacatona implies the shadow of the complementary family is at least m minus 1, m minus k minus 1, the baby form. Yeah, baby Cruz-Cacatona implies this. And this shadow is not quite on the case layer. So what we want to do is f lives on the case layer. We look at f bar here. You're going to keep, let me draw this picture. F is here. F bar is m minus k, k. You keep doing this shadow operation to get down to something here, which must be disjoint from f. F is here. Yeah, these two parts are disjoint, and the red one is large by Cruz-Cacatona. If you keep applying for the shadow, this is just going to be if you do the shadow one more time, this is bigger than what m minus 1, m minus k minus 2, right? You keep minus 1 on this until you drop down to case layer. So, when you apply this operation, m minus 2k times, you will see this is at least m minus 1 choose k. Good. But by this apple that I mentioned, all this shadow, which this is also k uniform, is disjoint from f, implying that the size of f is at most everything on the case layer minus a lower bound on this shadow, which is m minus 1 choose k. Low and before, this is m minus 1 choose k minus 1. We are done. Any question? Nice application of Cruz-Cacatona. Very good. Now, there's one more thing I want to talk about, which is related to this shifting technique and the new topic. Also important results in extremal set theory, this sour shell lemma, which is about a very important notion called VC dimension. This is what we're going to talk about next. So let's define what's needed. Okay, so what is VC dimension? Well, the question starts with you have some set systems. Some set systems, it could be a set of singletons. Okay, let's consider K-uniform set system on ground set N. Your K-uniform set system maybe just look like this. You take M minus K, N over K disjoint sets of size K. This system looks simple. Complexity is low. No sets intersect with another. Okay, you can compute everything about it very fast. On the other hand, what is the most complicated intuitively K system on N? It's everything, right? If you take all the K sets in it, everything, then it's complicated. It has everything. So what would be a good measure to quantify the complexity of the set system? This is what VC dimension is doing. So we want to, how can we measure, in a sense, the complexity of a set system? Okay. So intuitively, given the grounds, if our set system, let's say a K-uniform set system, it doesn't even have to be K-uniform, it's just any set system on some ground set, let's say N, could be non-uniform. Is complex if it contains sort of a large copy of itself. Okay, as I said, if you have a ground set, if you have all its subsets, singletons, triples, quadruples, then this system is complex intuitively. So if on some fixed ground set you have everything for some large R, then the complexity is quite large. And to make this rigorous, we have to talk about how the sets in our system intersect a subset of our ground sets. If this intersection could look very wild, then this system is very complicated. If this intersection could be all possible subset of R, the system is complex, right? If on the other hand, the intersection with the fixed sets intersection pattern is quite limited, then the complexity is low. So In other words, we want to look at how members of F intersect some subsets of the ground set. If number of distinct intersection is limited, then this is simple, not complex. If this number, there are many, then this is complex intuitively. To quantify this, we're going to define the trace of, do I need to define trace? Sure, let me define the trace. Given a family F on some ground set N, and given a subset, let's say S, subset of the ground set, we define the trace of F on S to be this all possible intersection pattern is denoted by F on S. This is all possible intersecting pattern with S. You take over all sets in your family. Now, if you have a large set S such that this trace is everything, we say that S is shattered by F. Now we can measure what we said earlier. When we say many, we mean completely shattered. All possible traces can be obtained. You have 2 to the S choices. Now we're going to look at the largest set S, its cardinality, which gets shattered. This will be the complexity we're going to use. That's how we make this rigorous. What we mean by contain a large copy of the cube. You should think of this as S, right? S of size R. What we really mean is the intersection pattern contains all possible subsets. And the largest such set S is the VC dimension of the family F. Actually, to be precise, I want to include the infinity case. So let me let the ground set be X, where X could be, so this could be infinity, infinite size, could be infinite sets. So we say if the VC dimension is infinity, if exist arbitrarily large sets, shutter sets. Okay. I have to. So here's an example. I will illustrate this example next time. I have to end the class a little bit early today. I'll encourage you to think about this example yourself before I reveal the answer next time. Is that if you consider x to be all the real numbers, so this is an infinite set, and you consider f, it's a collection of subsets of the real. So consider it to be all closed intervals, let's say. So that means it's A to B in R. Then the claim is the VC dimension of intervals, in this case, is 2. Okay, we will prove it next time. But try to do it yourself, and we can check it together next time. So what does it mean VC dimension is 2? That means we need to find 2 points on the real line as a set that gets shattered by closed intervals, meaning that you need to find 4 intervals, one containing both of them, one disjoint from both of them, one containing the first one of these 2 points, one containing exactly the second one of these 2 points. This is easy. And we have to prove that there's no larger shattered set. So you have to find 3 points such that you cannot completely shatter the 3 sets using closed intervals on real line. All right. So today we finished the proof of Kruskal-Katona. And we introduced the definition of VC dimension. All right, we will continue next week. So the next week, 2 classes, we're going to finish what we want to talk about on VC dimension, Sauer-Schaller lemma, and the last bit of the examinable material for the final exam will be these linear algebraic methods using a dimension argument to bound cardinality of a set of discrete objects. Then this is up to lecture 21.